Okay, so in this video, we are going to find the inverse Laplace transform of the function 3s minus 15 over 2s squared minus 4s plus 10. So we're going to need to do some factoring or maybe some completing the squares. So let me just pull out the 3 I can factor from the top, and what would be left would be s minus 5. And a 2 I can factor out from the bottom, and what's left is s squared minus 2s plus 10. Excuse me, not 10, plus 5. Okay, and then we can, again, assume that you've got this common Laplace transform table in front of you. Then you can try and look at the table and look at what we have here. And this doesn't really match anything in the table. So in the previous example, we were able to factor it and then use partial fraction decomposition. The problem is this quadratic does not factor. So that's not going to work. So we've seen that maybe completing the square might be a good strategy for this one. So let's take this function f of s and just rewrite it now as 3/2 times s minus 5 up top, and then in the bottom we're going to have an s minus 1 quantity squared, and the only way that we're going to get the 5 is if we add an additional plus 4 over here. So now we completed the square on the denominator. And if you're looking at the table of common Laplace transforms, then what you should see is that this seems to resemble one of these exponentials times a trig function. And so, in fact, what we've got very closely is looking at both of these denominators and comparing it down here. We have an a value, which is 1, and a b value, which is equal to 2, right? Because 4 is 2 squared. And so we almost have something that looks exactly like the cosine part, except if our value of a is equal to 1, then what I know is that I can write this as 3/2 times s minus 1 minus 4 all over s minus 1 squared plus 4. So I just took that minus 5 and broke it up because now what I have is an s minus 1 over s minus 1 squared plus 2 squared, which is exactly what I want if I want to use the inverse Laplace transform of the exponential times the cosine. But I still have 4 left over. And so if I take that minus 4 and write it like this, now I can cash in on knowing what the inverse Laplace, or at least what the Laplace transform of e times the sine function is. Okay, so all I did was I had this s minus 5 up top, which didn't match up anything that I have in the table. But I can take s minus 5 and write it as s minus 1 minus 4. So I'm going to use the s minus 1 for this piece so that it matches up the form for e to the at cosine bt. And now I still have this minus 4 left over. And that one I'm going to use with the constant divided by this stuff. But the constant b needs to be the same constant b over here. And so if we have a 2 squared down here, then my value of b is 2. So I only need 2 up here. But we had altogether a 4. So I can take this 4, use the factor 2 with the denominator to get the sine function out of here, and then just use the other multiple to as a 2, which is being multiplied by this entire expression. Okay, that's a pretty big mouthful there. But now, once we've got this, and I'm going to apply inverse Laplace transform to everything that we see, then we can pull that 3/2 out from the inverse Laplace transform. And then this first term, the s minus 1 over s minus 1 squared plus 2 squared, that's e to the a, which in this case is 1, t times the cosine of b, which in this case is 2t. And then over here, when I take the inverse Laplace transform of all of this stuff, the 2 comes down, and what's left is when I take the inverse Laplace transform of all of that, that gives me e to the at times the sine of bt, which again is 2t. So all of this stuff that we have over here is the inverse Laplace transform of the function that we started with.